Carbide burrs, those precision rotary tools made from tungsten carbide composites, generate significant heat during operation due to the intense friction between their fluted cutting edges and the workpiece, a phenomenon rooted in the fundamental physics of material interaction that can compromise tool life, workpiece integrity, and operator safety if not managed effectively. In applications ranging from metal deburring to wood carving, the burr spins at high speeds, often 10,000 to 30,000 RPM, creating shear forces that deform the substrate, converting mechanical energy into thermal energy through frictional sliding and plastic deformation. Thermal dynamics in this context follow the principles of thermodynamics, where the first law, conservation of energy, dictates that input work from the rotary tool's motor, typically 0.1 to 1 kilowatt, is partitioned into useful cutting, 20 to 30%, chip formation, 10 to 20%, and waste heat, 50 to 70%, with the majority concentrating at the tool chip interface in a zone as thin as 0.01 millimeter. Friction, the primary heat generator, arises from adhesive and abrasive interactions. As the burr's rake face, angled 5 to 15 degrees, slides against the workpiece, Coulomb friction, Mu equals 0.2 to 0.5 for dry metal on metal, produces tangential forces that elevate temperatures to 600 to 1,000 degrees Celsius locally, far exceeding the carbide's softening point, around 800 degrees Celsius for the cobalt binder, if unchecked. This heat flux, governed by Fourier's law, Q equals minus K dt over dx, where K is thermal conductivity, spreads unevenly, the low K of carbide, 50 to 80 watts per meter Kelvin, traps heat near the flutes, while the workpiece's properties, e.g., steel's 50 watts per meter Kelvin versus aluminum's 237 watts per meter Kelvin, influence dissipation, potentially causing work hardening, oxidation, or thermal cracking in sensitive materials like titanium alloys. The science of friction-induced heat in carbide burr cutting delves into tribology, the study of interacting surfaces in relative motion, where two main mechanisms dominate: sliding friction at the rake face, which accounts for 80% of heat via shear plane deformation, thickness 0.05 to 0.2 millimeters, stress 300 to 600 megapascals, and plowing friction from flute edges embedding into the material, generating localized hotspots that can exceed 1,200 degrees Celsius in microseconds. As the burr rotates, centrifugal forces, up to 50 G at 20,000 RPM, press the flutes into the substrate, amplifying contact pressure, 10 to 50 megapascals, and converting kinetic energy into thermal via Joule heating analogs with the heat partition ratio, beta equals 0.3 to 0.5 to the tool, determining wear rates. High beta leads to binder diffusion and flute erosion, reducing cutting efficiency by 40% over time. Material challenges compound this. In steels, austenite formation above 727 degrees Celsius alters microstructure, while in composites, resins volatilize at 200 to 300 degrees Celsius, releasing fumes and weakening bonds. Narrate the dynamics with an animated heat map. Envision a cross-sectional view of a burr engaging aluminum, initial contact sparking a red hotspot, 800 degrees Celsius, at the interface, waves of orange heat, 500 degrees Celsius, propagating along the flute like a thermal tsunami, with blue coolant lines quenching edges to green, 200 degrees Celsius. As friction builds, the animation shows unchecked heat blooming to yellow flares, 1,000 degrees Celsius, that warp the workpiece. But with mitigation, the map stabilizes in cool blues, illustrating how poor management accelerates tool blunting while strategies cap peaks for sustained performance. Strategies for heat mitigation begin with pausing techniques, which leverage convective cooling and conduction to the ambient air. H equals 10 to 50 watts per square meter Kelvin, allowing thermal equilibrium during brief interruptions that prevent cumulative buildup in prolonged sessions. The principle here is Newton's law of cooling, dT over dt equals negative HA. open parenthesis T minus T sub AM close parenthesis over open parenthesis, or HOCV close parenthesis, where surface area, A and pause duration, 10 to 30 seconds every 2 to 5 minutes, dissipate 20 to 40% of stored heat, particularly effective for Carbide's low internal conductivity that otherwise retains energy. Verbally guiding implementation. During deburring a steel bracket, engage the burr for 2 minutes at 15,000 RPM, then lift and pause for 20 seconds, fanning the tool or using compressed air to accelerate cooling from 400 degrees Celsius to 150 degrees Celsius, monitoring with an infrared thermometer to resume only below 200 degrees Celsius. This intermittent approach reduces overall session heat by 30%, preserving flute geometry and preventing bluing, oxidation above 300 degrees Celsius on stainless steels. For lubrication, synthetic cutting fluids or waxes, viscosity 10 to 50 centipoise, form hydrodynamic films that lower friction coefficients from 0.4 to 0.1, slashing heat generation by 50% via boundary lubrication, where the fluid shears under pressure to separate surfaces. Apply via drip or mist, 0.5 to 2 milliliters per minute, to the interface, choosing water-soluble emulsions for metals to enhance convection, K equals 0.6 watts per meter Kelvin, and flush chips, but avoid excess on woods to prevent swelling. Animate the effect. A heat map of a dry cut shows escalating red gradients, 900 degrees Celsius peaks, radiating from the flute, waves crashing into the tool like lava flows. With lubrication, blue fluid barriers interrupt the spread, capping hot spots at 400 degrees Celsius and diffusing heat evenly in green zones, the animation fading to stable yellows, clarifying how these strategies tame thermal chaos for safer, more efficient burr use. Advanced strategies integrate speed and feed adjustments with tool design, drawing on heat partition models, e.g., Jaeger's moving heat source theory, to distribute thermal loads away from the tooltip, where lower RPM, 10,000 versus 25,000, reduces frictional power, PE/SIF equals MU/FINV, with V as velocity, by 60%, though it may slow removal rates. Balance by increasing feed, 1 to 2 millimeters per second, for equivalent output. Flute geometry aids dissipation. Wider single-cut flutes, 0.5 millimeter spacing, vent heat via increased airflow, while double cuts enhance conduction through cross shears. For high-heat materials like titanium, K equals 22 watts per meter Kelvin, cryogenic cooling with CO2 jets, minus 78 degrees Celsius, flash freezes the interface, dropping temperatures by 400 degrees Celsius per studies in the Journal of Manufacturing Processes. Narrate a comprehensive map animation. In titanium cutting, an unmitigated scenario erupts in crimson flares, 1,200 degrees Celsius, engulfing the burr, material warping and animated ripples. Layer in pausing, waves pausing to cool. Lubrication, fluid veils quenching, and speed reduction, slower rotation diffusing peaks. The map evolving from volatile reds to controlled blues, with overlaid graphs showing temperature curves flattening from exponential rises to linear decays, educating on the multifaceted science that keeps carbide burrs performing optimally. In the realm of carbide burr use, heat management intertwines thermal dynamics with practical strategies, where friction's inexorable generation of energy demands proactive mitigation through pausing for convection, lubrication for boundary separation, and tuned parameters for balanced loads. Animated heat maps bring these concepts to life, visualizing the perilous escalation of hotspots and the calming interventions that preserve tools and materials, ensuring safer, more efficient operations grounded in the elegant physics of heat transfer and tribology.